Hello friends, in this video I'd like to solve the following problem from the International Mathematical Olympiad 1980, shortlisted problem 26, which was proposed by Yugoslavia. So it was shortlisted, it was not actually given to the participants, but it was considered to be given. We wish to show that any function f from the set of real numbers into itself satisfies Cauchy functional equation, that is f of x plus y equals f of x plus f of y for all real numbers x and y, if and only if f of x plus y plus xy equals f of x plus f of y plus f of xy for all real numbers x and y. So in other words, these two functional equations are equivalent. It's a nice problem. Here are my hints. First, one implication is pretty trivial. For the second implication, assume that our function satisfies our second functional equation and do the following. First, set y to be minus x to justify that our function is odd. And then, crucially, the second step is crucial. Assume that x is not minus 1, z is any real number, and set y to be z over x plus 1. And then you should get some equation in terms of x and z. Try changing z to minus z to justify that this equation f of x plus z plus f of x minus z equals 2 times f of x is true for all real numbers x not equal minus 1 and all real numbers z. Then set x to be z to show that f of 2x equals 2 times f of x for all x is not equal minus 1, then let a be equal x plus z, b equal x minus z, to justify that our function satisfies almost Cauchy functional equation, almost, because we know that it is satisfied if a plus b is not equal minus 2. And finally, consider this very last case separately. What happens when a plus b equals minus 2, using the previous result. So give this problem a try, and I will see you in just a minute. All right. So let's do first. Let's maybe mark this equation asterisk, this equation double asterisk. First, I will prove that asterisk implies double asterisk. This is the easy implication, because notice that f of x plus y plus xy, well, using our condition asterisk, it can be written as f of x plus y plus f of xy. And using our condition asterisk once again, we can split our first term into f of x plus f of y plus f of xy. And that shows that our condition double asterisk is satisfied. Now, much more interesting is the second implication. 2 asterisks imply 1 asterisk. So first, let's set y to be minus x in our condition double asterisk. Then we have the following. Well, on the left-hand side, we have f of xy, because x plus y is 0, equals f of x. F of y is f of minus x plus f of xy. Or maybe let's put instead, because y is minus x, so we have minus x squared minus x squared. And we can do cancellation, and we get the following, that for every real number x, f of x equals minus f of minus x, i.e. our function is odd. Our function is odd. Let's remember that, and let's call this a condition maybe triple asterisk. Our function is odd, and in particular, since f is odd, f of 0 is 0. Let's also keep that in mind. And now comes the nice part. Let's now consider let x be not equal minus 1, let z be any real number, and set y to be z over x plus 1 in our condition asterisk. Then it becomes the following. On the left hand side we have x plus y, but y is z over x plus 1, plus xy, but xy is x z x plus 1, equals f of x plus f of y plus f of xy. And notice that this choosing that y should be equal z over x plus 1 is justified by the fact that on the left hand side, if we combine these two terms, we will get z x plus 1 over x plus 1, which is just z. Yes, it was the motivation behind this substitution. So we have the following equation. F of x plus z equals f of x plus f of z x plus 1 plus f of x z x plus 1. Perfect. And now let's take the previous line and let's change z to minus z, and we have then f of x minus z equals f of x plus f of minus z x plus 1 plus f of minus xz x plus 1. And now let's take these two equations and let's add them together. Adding 1 dot and 2 dots together, and we have the following. On the left hand side we have f of x plus z plus f of x minus z equals 2 times f of x, and now we have f of z x plus 1 plus f of minus z over x plus 1 plus f of x z over x plus 1 plus f of minus xz over x plus 1. And now we'll make use of the fact that our function is odd, because these two terms are 0 and these two terms are also 0, because our function is odd. Because it is odd. And we have now the following equation, and I will put quantifiers for every real number x not equal minus 1, and for every real number z, f of x plus z plus f of x minus z equals 2 times f of x. And let's call this equation, I don't know, square, condition square. All right. We are almost there, but not quite yet. And now let's set x and z to be equal and not equal minus 1 in our condition, which I marked square. Then we have the following. On the left hand side, we have f of 2 times x plus f of 0 equals 2 times f of x. But recall that f of 0 was demonstrated to be 0, so we have f of 2 times x equals 2 f of x. Right, and now I need a new page, so give me a moment. Right, And now our condition square becomes the following. Instead of 2 times f of x, we can put we can write f of 2 times x, and also quantifiers for every x not equal -1 and for every z real. Perfect. And now I will consider the following. Let a be equal x plus z, and let b be equal x minus z. Well, then notice that if we add these two equations together, we get 2x equals a plus b. So we get the following. We have the following. For every real numbers a and b, if because remember that x cannot be -1, so a plus b cannot be -2. If a plus b is not -2, then f of a plus f of b equals f of a plus b, which is exactly what we want to show. But we have this one obstacle left. We have to consider now what happens if a plus b equals -2. So consider now a and b which are real and whose sum is -2. Well, then that means that b can be written as -a -2. What do we have? F of a, maybe I'll write it in white, f of a plus f of b equals f of a plus f of -a minus b. All right. And now I wish to consider first, using the fact that our function is odd, we can write f of a minus f of a plus 2. And now I wish to split this into f of a plus f of 2. Can it be done? Let's take a look. It can be done if a plus 2 is not -2. So it can be done, or maybe, you know what, no. Let's do it already in this step. Sorry about that. Let's do it in this step. This can be split into f of -a plus f of -2. Of course, this is true if a minus 2 is not equal -2. Yes, I'm using this condition right here. If a plus b is not -2, we can split it into these two terms. And that is, notice that is exactly, now we will use the fact that our function is odd. So it's f of a minus f of a plus f of -2, which is f of -2, which happens to be, of course, f of a plus b. So now we are using here f is odd. To put this minus in front. All right, but it works very well if -a -2 is not equal -2. So we have one final case to consider. If -a -2 equals -2, i.e. if a equals 0, then we have the following. F of a plus b is just f of a, and f of a is, of course, f of a plus f of 0, and it's f of a it's f of a plus f of b. So in this case, it also works. In every case, we have demonstrated that in every case, this condition right here is satisfied. Yes. So we have demonstrated that for every two real numbers a and b, f of a plus f of b equals f of a plus b, which is exactly our condition asterisk, which we wanted to demonstrate. And that closes our proof. So that means that two asterisks imply one asterisk, and that closes our proof. Very nice problem, I'd say. Very nice problem. So thank you very much for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.